Subir is here. Hi, Subir. Can you hear me?
Hello.
Hello, can you hear me? Let me put
Yeah.
my
It's good to see you.
Okay, can you hear me now?
Yes.
Yes.
Okay, good morning. Hey,
Morning.
How are you? Good morning.
good.
So maybe we can test. You can
Yeah.
whether you can share.
Right. So let me start. 1 second. I also want to use a different mouse.
Okay, seems like it works.
Does that look good?
Yeah. Oh, yeah. Works.
Can you see the green pointer that I'm moving
Yes.
on the screen?
Yes.
Yes.
And you can hear me okay?
Yeah.
Mhm.
All right. Okay.
It's working. Yeah.
How
Yeah,
are
I
you
wish-
doing? Yeah. It's almost
Hi,
7
Sam.
p.m. there. Yeah.
Yeah. Yeah, busy day. I don't know. I don't know why I agreed to give 5 lectures. You're going to have to listen to. Don't have to. But I was preparing them today. So really busy.
So I already saw your slide for tomorrow's lectures.
For the first one.
Yeah.
The second one. That was a brand new talk, so it took some time. The others, I can cut and paste from old talks. I hope. Let's see.
I'm sorry that we have this webinar format. So I think the usual one
Yeah.
could be easier to
Right.
communicate. But since I heard
Yeah.
some stories about this unpleasant this June bombing,
Yeah.
so that
Right.
so that I think it would be better to be safe.
Right. So you're all at home, or you're all at institute, or?
I'm at the office. I think most of
Good,
people
yeah.
are at home.
I'm home. I'm currently self-quarantine situation. I just
Oh,
came
you
back
had
to
to-
Korea. Yeah.
Okay.
Yeah, I'm home too. Yeah.
I'm trying to figure out if your background is real or virtual. Sounds in-
Yeah.
Me too. actually.
Disney animation.
Oh, is it? Okay. Looks
Yeah, I
nice.
downloaded.
Ah. Well, this is my home office, so this is where I've been teaching for more than 6 months from this desk.
So you often go to school, or I heard Boston University is not online, the lectures.
I don't know about Boston, but Harvard is completely online. I'm not even allowed to go to my office. I have to get
Oh,
special
you're not
permission.
allowed.
Well, I can, if I want to pick up a book or something, I have to get a permission, and I can go and pick it up.
Oh, wow.
But yeah, it's still pretty strict. And but the labs are functioning. People who are running the labs are allowed to go and operate the labs. In fact, I'll show some data that was taken tomorrow on Rydberg atoms during the pandemic.
Wow.
So only the experimentalists can attend to their lab and do the experiments, but not the theorists.
Yes.
Theorists are all screened out. Screened out.
Well, I mean, we can function via Zoom, right? So
Right.
that's what we are supposed to do. Yeah.
KAIST is also for this spring upcoming this spring semester. It's everything is online, I think.
I thought things had gone down in Korea, but then they started coming back up. Or...
Yeah, the situation is much better than the States, but still like 500 people per day.
500 people are infected.
Infected for the entire, Korea.
Massachusetts, it's more like, just for Massachusetts, is infection is about 2,000, 3,000 people per day.
Yes.
And even now it's about 50, 60 deaths per day.
Oh.
Wow.
That's down. It was more like, just a month ago, it was more like 150 deaths a day. Yeah.
Have you got shot the vaccine?
Not me. I'm very low priority.
Okay.
But, my father, who's above 80, he got shot. He's got, and my daughter, who's a doctor, she's gotten shot. So, but not me.
Yeah, so people are coming, and I think we will start probably 9:05.
Okay.
To wait because it's 9 a.m. To some people, it's not that early, but to some other people, it's quite early time.
The physicists are very early. Yeah, whenever I teach a 9 o'clock class at Harvard, nobody comes.
So in this sense, it's good to have time difference.
Okay.
So this colloquium and lectureship series is supported by mainly two programs. One is this KAIST from KAIST, and the other one is NRF. And Gil and Songbin and Youngbook Kim, I think he's here also. We are a group of people who are, so it's group funding.
I see. Oh, nice. Okay.
Ungguk is the
NRF,
boss.
it's a national. It's a different institute, or it's just a.
It's not different institutes. Just four of us forming a group and want to study some research topic related to this ultra quantum matter.
Okay. Yes. Leon came up with that name.
Oh, Leon. That was Leon. I see. Maybe next speaker, you should ask Leon to join. And Kwon Park, he kindly joined us because I will ask him to chair the whole session because I wanted to ask Songbin, but Songbin is in self-quarantine right now. So
sorry.
So if something happens, then who knows? So I asked Kwon, and he kindly accepted. So he will chair the tomorrow session, and Gil will be the chair of the last day session. And of course, I'll be here. And but the reason
and my talks will be recorded, right?
Yes.
I guess I can see it's being recorded. Yeah. So I'd like to get a copy of the recording whenever.
So we need to discuss about that actually. So do you mind we kind of open your talks, or we share your talks online or public in public?
I don't mind. Yes. No, please do. I don't mind at all. Yeah, go
Mhm.
ahead and share it.
Mhm.
As long as I get the link, then I can also put it on my webpage
Mhm.
for my students to look at.
Okay. So people keep coming. So I think most people. To the audience or attendees or panelists, if you have any question, please raise your hand, and right, or you can use Q&A. I think I do not allow chatting right now, just in case. But if you want to chat or if you want to ask question, please use Q&A. I think that will be more effective. Panelists, you cannot use Q&A. So
Yes, I know.
so that you can just unmute
So-
yourself. But
Okay.
so probably if there are questions on Q&A, I'll stop the talk Spear, and then I'll tell you about the question, and you can read. So during your presentation, you can answer questions if there are many questions. Then I will try to moderate.
Okay, sounds good.
Okay, so keep coming.
It's just chatting.
It's 9. Maybe in 2 minutes or 3 minutes, we'll start. Some high energy theorists or astrophysicists who are working on black holes, they also want to join. I'm not sure how many people are joining here.
Yeah, well, so my first lecture will, I mean, it'll be fairly basic for physicists, I think. But my third lecture will, we'll go into some actual quantum gravity.
Mhm.
What little I know. Yeah.
Yeah, so it's already over 100 people. I think more people are coming.
I guess we can slowly start.
Spear is okay.
Yeah, please go ahead.
Okay.
Should I? Well, let me know when I should share my screen.
Okay. We can get started. So welcome everyone to our distinguished colloquium and lectureship series, which are supported by KAIST Advanced Institute for Science, Science X actually. In short, we call this the KAIST program, and the Beijing Research Laboratory funded by National Research Foundation of Korea. So it is great honor for me to introduce the first speaker of this series, Professor Subir Sachdev. Professor Sachdev is a Herschel Smith Professor of Physics at Harvard University, who specializes in theoretical physics, not only condensed matter, but also all kind of strongly correlated system, including ultra-cold atoms, statistical physics, and also even black hole physics. Professor Sachdev has made important contributions to the modern understanding in entangled phenomena of quantum many-body systems, let me briefly introduce a few important accomplishments. Professor Sachdev has provided very nice perspectives in strong Correlate system, which apply to not only pure theoretical problems, but also phenomenological problems. One of the key examples, I would say, is quantum criticality and its role in interplay physics between conventional order parameters and topological orders. This perspective successfully is applied to many Correlate systems, including quantum magnet, quantum antiferromagnet, especially graphene, readable atoms, and iron and copper-based high temperature superconductors. Professor Sachdev also invented new theoretical methods to study strongly Correlate system. For example, the bond operator mean field theory and the Bijon mean field theory. And moreover, Professor Sachdev proposed new universality class beyond the Landau-Ginzburg-Wilson paradigm, so-called deconfined quantum criticality. He also proposed an exactly solvable model, which transforms to the so-called Sachdev-Ye type model recently. And I believe that we have a chance to listen about this nice model and associate phenomena with the black holes. With this accomplishment and the other ones, which I do not have a chance to mention, Professor Sachdev received numerous awards and also was elected to the US National Academy of Sciences. The prestigious awards include the Lars Unsager Prize from the American Physical Society and the Dirac Medal from International Center for Theoretical Physics. I only name a few things about his accomplishment, and I can spend more time and more time to explain. But I believe it is also very important to listen his words in his colloquium and lecture series. So I'll stop here and be ready to listen to the colloquium. And I'm delighted to have a chance to introduce Professor Sachdev to KAIST and Korean community and even Asian communities. And I wish to say that it is my great honor that I had a chance to spend time with today's speaker when I was young. Let's welcome Professor Sachdev.
Okay, thank you very much, Jungkook, for a very kind introduction. Very flattering, but it's really good opportunity for me to meet you and all these friends in Korea, and you're going to get, and talk about some of my recent and not so recent work. So thank you very much, and I hope there'll be a chance to visit Korea in not too distant future. All right, so let me share my screen. Okay, and oh gosh, where is my? I guess you're seeing my. All right, so I hope you're all seeing my slide and the green pointer and can hear me clearly. If there's any issue, let me know, Jungkook. All right, so let me then begin. So as Jungkook mentioned, I am going to be talking about a simple model of many particle entanglement and give you some fairly elementary description, I hope, of its connection to different fields of physics, including superconductivity and black holes. I've tried to make the talk accessible to undergraduate students in physics, although there will be one or two slides where I'll get a bit more technical, and I'll warn you when that's there, but hopefully you'll be able to follow the main ideas. All right, so let me just begin by this article from the New York Times in 2015, which had a nice title, "Sorry Einstein, Quantum Studies Suggest Spooky Action is Real." So the spooky action is a feature of quantum mechanics that apparently Einstein called spooky action at a distance. And it's a rather bizarre feature where measurements of quantum degrees of freedom in one part of space instantaneously influence the state of different particles in a different region. And in this particular experiment, there were two photons, little quanta of light, which was separated, and the observation of one influenced the other. So Einstein thought this would never really work, that there was something wrong with quantum mechanics because the spooky action seemed just so bizarre. But we know today that that is definitely real, and we have a very different perspective on it. It's not viewed as a bug, but really a very important feature of quantum mechanics. It leads to all kinds of interesting effects that many of us are studying in different fields of physics, and I'll try to give you a flavor of that today. All right, so the more formal term for spooky action is quantum entanglement. And what is quantum entanglement? So the basic idea here is to generalize the idea of quantum superposition to more than one particle. So I'm sure you've all heard about the basic idea of quantum mechanics, that a particle can be in two places at the same time, or more humorously, a cat can both be dead and alive. But if you take that idea of superposition and apply it to more than one particle, you immediately are forced to consider the feature of entanglement. So for example, if I consider a hydrogen molecule, it's made up of two hydrogen atoms. We have a nucleus and an electron. I'm just going to represent the electron by an arrow, which is supposed to point either up or down. And the arrow tells us whether the electron is spinning clockwise or counterclockwise. And so this is a hydrogen atom with the electron spinning clockwise. Now what happens when you take two hydrogen atoms and put them in a molecule, then very roughly speaking, you can think of the electron forming this state here, where their spins are always anti-parallel. If one electron is clockwise, the other is counterclockwise. So this is up, this is down, or vice versa. But neither is determined. It's really a superposition where this first electron is either up or down, and the actual state is a superposition of up, down, and down, up. So this particular combination is called an entangled state of two electrons. Okay, well now, that's a reasonable thing, which was understood already in the very early days of quantum mechanics. But Einstein, Podolsky, and Rosen proposed a thought experiment where you imagine that you take this tiny little hydrogen molecule, and by some very clever experiment, you separate the two electrons. And you separate them in a way that you don't disturb how they're spinning, which means practically you have to make sure that there's no magnetic field applied on the electrons. So if you can do that, then as you separate them, the entangled nature of the electron spins will persist. It has nothing, since you're not measuring the spin, you're not disturbing the entanglement. So in principle, this electron could be with me and the other one could be in Korea, and they would still be entangled. So the state of the pair of electrons is not determined. I could have either up or down with me, and vice versa in Korea, but it's not known until you look at it whether I have an up or down. In fact, if I look at this electron randomly, I'll see down, and at that very instant, I'm sure that the other electron has so-called collapsed into the up state. And so this is the non-local spooky action that was tested in the experiment I briefly mentioned. All right, so that's the basic idea of entanglement, and sometimes it's called the Einstein-Podolsky-Rosen paradox. That how could this possibly happen? Measurement of one particle instantly determines the state of the other particle arbitrarily far away. But not only does it happen, it's not a paradox. There's no logical feature that you've violated. The one thing you have to accept is that the idea of a quantum state, if you want to describe a set of particles, or these pair of particles here, the idea of the state doesn't live or reside with one or the other particle. It's neither here nor in Korea. It's really nowhere. It's a non-local idea that specifies the state. So but other than that, physics is still local. What I do here influences what's happening here. It's just that because these two particles had interacted in the past, they share a state, and you can perturb that state either here or there. Okay, so that's a very quick summary of quantum entanglement. And so now what we want to do, really the whole purpose of this lecture is to talk about many particle quantum entanglement. I want to go from not just 2 particles, but really an infinite number of particles, and ask, what does quantum entanglement do there? Now, this is still a new subject. We don't fully understand and classify all types of entanglement of many types of many particles. But I'll give you a flavor of some of the things that people are working on. So one place, and this will be done in the context of this many particle model, sometimes called the SYK model. So one place you have many particles influencing each other is in metals. So an ordinary metal like aluminum or iron they all have common features, like they're shiny, they conduct heat and electricity efficiently. And the reason for that is that in metals, each atom donates a few electrons, which are delocalized throughout the entire material. So you have lots and lots of electrons running around. And as they're running around, they can feel each other because of their electrical charge. They repel each other. And that can cause entanglement between the electrons. And that's kind of what we want to study. Now, it turns out, however, in most metals, this entanglement is not such a big deal. And the reason it isn't is because of something called a quasi particle. So here's a bare electron running around the wire. Of course, it's interacting with the electrons around it. But it turns out that if you take a material like aluminum or sodium, the interaction of the other electrons around this electron doesn't do much other than give a cloud around it. So that instead of being a bare particle, it's what we call a quasi particle. But as long as you don't look too closely, this quasi particle behaves as if it's just an ordinary electron. So there is a little bit of entanglement here, but it quickly dies away. And then it's as if you have free electrons, which are not entangled with each other, moving around in this quasi-particle concept. So the existence of quasi-particles implies limited many-particle entanglement. And that's the reason, really, the study of entanglement is a modern subject. I mean, people have been studying metals for 100 years. Using quantum theory, and they've never really needed to think deeply about entanglement because the quasi-particle theory is extremely successful. Okay, so one way I want to quantify this, the fact that the entanglement is limited, and one way to quantify it is to characterize it by a time, and this time is going to play a fundamental role in many things I'm going to discuss. So if you have electrons moving around in this wire, they will collide with each other, and eventually the quasi-particle will, no longer remain a quasi-particle, collide with other quasi-particles and forget where it came from. So there's some typical time it takes for one quasi-particle to scatter off of the other that we call tau. And now the key feature is that in ordinary metals, where you have current flow with quasi-particles, this time is much longer than a very basic time, which is called the Planckian time. That's going to reappear in my talk many times. And it's a time that you build out of the temperature. The temperature tells you something about how energetic the electrons are. Kb is Boltzmann constant. Forget about it. It's just because we insist on measuring temperature in strange units of Kelvin rather than energy, we need it. But so just ignore the Kb. And h bar is the famous Planck's constant. So it turns out, which is just a fundamental constant of nature, which affects, how quantum everything is. So this is known, and temperature is a basic quantity. And this particular time that you can build out of temperature is called the Planckian time. So for the quasi-particles to be well defined, you don't have to scatter too much. If they scatter a lot, then basically it's as if the quasi-particle didn't exist and everything is entangled with each other. So the consistency of the theory requires that when the electrons are not too entangled, their scattering time is longer than the Planckian time. Okay. All right, so that's a quick summary of what is normally taught over a year or two in a solid state physics course, but I hope the basic idea is quite simple and clear. All right, so that's in some sense, the enemy. That's what a typical material will do in the lab. It's kind of boring. There's not much entanglement. All right, so now I'm going to give you a simple model, which has, in fact, as we're learning, in some sense, a maximal type of entanglement. So this is just what we call a toy model. It's not something actually describing anything in anyone's lab, although people are trying to build it now. So you just take a bunch of positions, chosen at random, and then you take a few electrons. Here I'm ignoring the spin of the electrons and put them randomly on some of the sites. So this is one possible quantum state with the electrons occupying the purple sites. And now we have the electrons, because of the structure of these sites and the various potentials they experience and the other atoms that are around, there'll be some amplitude, as we call it quantum mechanically, for the electrons to move around. So every possible transition from one state to the other is governed by some number. And normally, if this was a metal or some kind of metallic dot, then the electrons would basically randomly hop from site to site with some amplitude and interfere their individual paths. But in this SYK model, you don't allow them to do that. You just turn off what we call one particle hopping. So what you allow, however, is two particle hopping, or more than two, but two is the important minimum. So for example, these two electrons have a certain amplitude whose square is the probability, quantum mechanically, to go from here, from these two sites to those two sites. In fact, you don't know which electron is which, so it could be either way, and they end up there. Okay, so that particular process has some number associated with it, which depends on all the details of the system that you've devised. And once the electrons have hopped together, in a sense, they're entangled because their wave functions are now connected to each other. Okay, and what is the amplitude for that process to happen? Well, the key feature of this model is as simple as you can imagine. You just make it a random number. So you pick another pair of particles like those two, and they can exchange, and that has another process that's allowed, and so on. So basically, as long as you're obeying the exclusion principle, which says that two electrons can't occupy the same site, anything that's allowed will happen. And how often will it happen? Well, it'll happen with a random probability. So each process has a fixed random amplitude, and all of them are allowed. And that's basically the full description of the SYK model. And because of these random pairwise hoppings, all of the electrons are starting to get entangled with each other. And what we now know is that under such a situation, they really form a new type of quantum state, which is quite unlike what you see in ordinary metals, which does not have any quasi-particle description. So it's some kind of very entangled state. All right, and a few more. Okay, you can get tired of this, but you can see there are many things that are allowed. So here is just one slide for the more technically inclined. This is how you write it out in the physicist operator language. These electrons is here. This is a term that tells you that electrons hops from site K and L to site I and J, and this is the amplitude of this number, and that number is a random number with mean square value U. So, and the total charge of the electron, the total charge of the system is just the sum over all the electron number operators on every site. Okay, so that's the model. Don't worry about if you find this, haven't seen these operator stuff before. Anyway, so that model, it turns out, quite amazingly, can be solved. You can actually work out all kinds of properties essentially exactly. And remarkably, you can work it out because of the randomness. If I gave you a specific set of numbers and say, I built this system with this number, and this is 5, and that's 2, and this is 1.7, and that problem is impossible to solve because it would require too big a computer than we have. However, if I just tell you the random numbers, then you can solve it quite remarkably. Okay. And what do you find when you solve it? Well, you find the exact opposite of the boring metals I talked about earlier. You get a metallic state, which can have electrons moving around, but there are no quasi-particles. So what are the excited states? What are the excitations above the lowest energy state? Well, I can't think of them as quasi-particles moving around. It's some very complicated modification of the entanglement between all the electrons. So in some sense, in this model, the electrons are all, in a very complex manner, entangled with each other. And one of the consequences of this entanglement, yes, there's a question?
There is a question.
Yeah, please, go ahead. Let's see, I have to look at the Q&A box.
Or I can read it for you. Can an electron
let me, no, I am just finding looking for. Okay, the question is, can an electron hop more than 2 sites, or just 2 sites is allowed? You can hop, you can have 3 electrons hop together, or 4 electrons hop together. It won't change anything. The important thing is to just prohibit 1 electron hopping on its own. Okay. All right, so then let me see, how do I close this thing there? Okay. All right, so yes, so I was talking about this. All right, so you can quantify this absence of quasi-particles. And the one way to quantify it is to do exactly what you do in a metal. That is, you try to drive some current, or you push the system, and you ask how long does it take for things to just equilibrate, just become totally random, to thermalize. So in a metal, that would be the time tau, which was much longer than h power over kt. In this system, you'll find it's exactly of order h power over kt. And in fact, there's a number here that you can compute also precisely depending on exactly what type of probe you're making. So you'll find here, you saturate what's the Planckian bound for equilibration and also for the system to become chaotic. And that's really the key property of this system with many particle entanglement. And remarkably, as we'll see, the same properties appear also, have been known also for a while when we think about black holes. All right, so here's one of the, I'm going to wave my hands a lot with a lot of claimed results and connections, but at the heart of it is a very precise mathematical result, which I will state. So we compute what's called the partition function of this system at a temperature T. This is just a way of computing the thermodynamic properties, in particular its entropy. And the partition function is, roughly speaking, the exponential of a quantity related to the entropy. And the answer turns out to be this. And my third lecture will fill in the missing steps between the first and the second equation. But let me just describe the structure of the thermodynamics of this problem. So it turns out there's a large low temperature entropy. So in the 0 temperature limit, there's entropy, which is of order e to the n. And what this tells you is that there's many states very close to the lowest energy states, an exponentially large number of them. And this is because of the exponentially large number of ways you can rearrange the entanglement of all these particles. In an ordinary metal, you get much fewer states at low energy because you have to build them out of quasi-particles. And it'll turn out that this entropy of this set of entangled particles is a good model and one way of thinking about the Hawking-Bekenstein entropy of black holes. And that's something I'm going to talk about very shortly. Then there's a correction as you raise the temperature to the entropy, this temperature-dependent correction. And this will also be connected to black holes. And this correction is expressed as what we call a Feynman path integral. So quantum mechanically, Feynman showed us that you can think of the amplitude of a particle to go from here to there as the sum over all possible paths that particles could take, with each path given an amplitude. And this is very much the same thing, except instead of summing over paths of a particle, what you sum over are reparameterizations of time. So think of some time that's telling you how these particles are evolving under the Hamiltonian. And you have to sum over all possible ways of clocks running fast and slow. And that's, as you can see, that's a very natural feature of gravity, of quantum gravity, where you have to sum over all possible metrics of space-time. So in this case, there's no space, there's just a time, and you have to sum over all possible reparameterizations of time. But then what's the amplitude for each one of those time reparameterizations of different, when the clock's running fast and slow? The amplitude turns out to be something that you get from Einstein's theory of gravity, but in 1 + 1 space-time dimensions. And so if you do a quantum theory of gravity in 1 + 1 space-time dimensions, and try to sum over all possible configurations of space-time in a sensible way, you find that sum over all possible configurations of space-time and the theory of gravity is essentially exactly the same as the path integral you need to evaluate to figure out the spectrum of the low energy states of this many particle entanglement. So, in some sense, this model that I showed you becomes equivalent to a model of gravity in the sense they have describe the same set of quantum states, but they're of course represented in very different ways. And this equivalence between gravity and 1 + 1 space-time dimensions, which is 2D, and this model which really has no space, it's just everything is connected to everything, which is in say 0 + 1 dimensions. And that's why you call this is an example of what's called holography, where you're taking a higher dimensional object, which is quantum gravity in 2 dimensions, and making a hologram of it. And the hologram of quantum gravity in 2 dimensions is, in fact, the SYK model. This is a particular type of gravity, which, of course, I will say more about in my 3rd lecture. And a little bit more later today. Yes?
There are 2 questions.
Okay. Okay, so one question is, this model neglect locality completely? For what class of matter is this model good? Okay, that's an excellent question. Let me defer that to the end of my talk today. Right now, this is just a model. It's a toy model, as you call it. It's cooked up to have some fun. I'm not applying it to anything yet. Second, that entropy is thermal entropy, or can it be related to quantum nature? Yeah, so it is a thermal entropy, but it's also connected to entanglement entropy, and I'm being a little sloppy in that distinction today. Okay. All right, so I've described anyway this toy model, this SYK model, and as I'll say more in my 3rd lecture, if you compute its low temperature thermodynamics at low temperature, which means you just simply count all the states at low temperature and how they interact with each other, you find that it's in fact, quite surprisingly the same as the theory of quantum gravity in 1 + 1 dimensions. So now I'm going to tell you more about quantum gravity so that this hopefully won't seem as surprising. Okay, so to do that, I need to tell you a little bit about black holes. So what are black holes? So black holes, first discovered by Schwarzschild as solutions of Einstein's theory of general relativity, and they were such bizarre objects that appeared from the theory that nobody really believed that they were actually true. And since then, we realized that not only are these solutions reasonable, there are black holes out there everywhere in the universe. Every galaxy has a supermassive black hole at its center, and they're now routinely studied. And in fact, last year's Nobel Prize was given for the detection of the massive black hole at the center of the Milky Way. Okay, so a black hole is basically an object so dense that light itself cannot escape from inside what's called the horizon. So if you take an object of mass m and you squeeze it down to a radius smaller than the horizon radius r, then the gravitational pull of that, whatever the mass m that's sitting here, will be so strong that if an atom emitted a beam of light, the light would just come around and come back to the center of the black hole and collapse. So the escape velocity of any object from the black hole is bigger than the velocity of light, and since nothing can travel faster than velocity of light, you get a black hole. In fact, if you just use Newtonian mechanics and just put the escape velocity in Newton's gravity equal to velocity of light, you will also get the same radius coincidentally. Okay, so there's a region inside the horizon which is causally disconnected from the rest of the universe. It can never, at least in Newtonian and Einstein physics, communicate with anything outside. And once you fall into a black hole, basically you're done for. No information, nothing can ever escape. Okay, so that's what's called the classical theory of gravity, including the Einstein relativistic corrections. But now we've introduced Planck's constant. And the people who first started thinking about quantum gravity and realized something bizarre in black holes were Bekenstein and Hawking. And today we can cast the arguments in terms of entanglement. So we take my favorite pair of entangled electrons, and instead of separating one here and one into Korea, let me throw one inside a black hole. So I keep one electron here outside, and I send the other one into the inside of the black hole. So really there's no, and that electron is lost forever for me. But there's really nothing special on the horizon. Falling through the horizon, I won't even know that I'm falling through the horizon if I was falling into the black hole. So you fully expect, from what we understand about quantum mechanics and gravity, that these two electrons are still entangled with each other. So there is something we know about the inside of a black hole, quantum mechanically. So if I look at my electron here, I know that electron that I send in, before, of course, it crashed into the mass of the center, had the opposite orientation. So immediately you see that the black hole horizon is a bit leaky once you have quantum mechanics. But it's really much more leaky than people realize. So there's quantum entanglement between the inside and outside of a black hole. And what Hawking showed was that this means that black holes actually radiate and evaporate like a cup of coffee. And eventually every black hole, if you wait long enough, will disappear into just radiation that comes out from the black hole, which is called the Hawking radiation. And roughly speaking, how can I understand this? So of course, I won't go into the details of the quantum process here, but the basic idea is if I am sitting here and my qubit is out here, and my electron's here, and the other one, which was entangled, is inside, since I can never find out what that other electron is doing, since there's no real information other than this entanglement that can go across the horizon, as far as I'm concerned, this qubit is just random. This electron is randomly up or down because that other electron is causally disconnected. And so that's equivalent. So when you have something random, that's equivalent to temperature. Okay, so that's just a very simple argument. Of course, it's not the complete argument, which sort of gives you a flavor of what Hawking argued. And Hawking, in fact, computed the value of T sub h. So black holes have an entropy and a temperature, which I'll call T sub h. And they also have an entropy because of this random qubits, the random electron that I have. That's called the Bekenstein-Hawking entropy because Bekenstein proposed it earlier, although he didn't compute its precise value. But what both Bekenstein and Hawking showed was that this entropy is proportional to the surface area of the black hole. And why is that? Well, that's also quite simple because it's the entanglement across the horizon that's giving you this entropy, and therefore it should be proportional to the area of the horizon. All right. Sorry, the other way. Okay. So So that was the conclusion in 1974 by Hawking and Bekenstein. And it immediately launched kind of a revolution in physics, because this is totally bizarre. Because if I take any quantum system that I know, even today, as long as I'm not worrying about quantum gravity, they have an entropy proportional to their volume. You know, if I have a cup of coffee, its entropy is proportional to the volume of the coffee. It has nothing to do with the surface area. But this seems to be an exception to that rule. Once you put in quantum gravity, somehow entropy is proportional to the area. And I gave you, a feel for why that may be the case. Now, this is, of course, understood much better today from the idea of what's called holography. And string theory in particular gave an explicit realization of how this happens. And it's related to what I already mentioned with the SYK model, which is that because black holes have entropy proportional to surface area, they're equivalent as a hologram to a quantum system without gravity, some kind of strongly interacting quantum many-body system, in particular a system that won't have quasi-particles, as we'll see in a minute, in one lower dimension. So you project from 3 to 2 in this case. And so you would say that if I really wanted to describe all the quantum mechanics of a 3-dimensional black hole, I could equally well study some very complicated systems of quantum degrees of freedom, quantum many particle system, which lives in 2 dimensions. So that's the basic idea. I think people like Susskind were discussing it quite early on. And then in a very beautiful work, Maldacena showed how string theory gave an explicit example of this holography. Okay, so now I want to tell you one more feature about black holes. And just for fun, I'll show it to you in terms of some actual data, which doesn't actually measure that. So this is the famous observation of gravitational radiation by LIGO. What LIGO observed was the merger of 2 black holes, each of which had 30 solar masses, about 1.3 billion light years away. And here is the gravitational signal that was observed on Earth. And this particular, these oscillations represent the gravitational waves that are emitted as these 2 black holes in spiral merge and form a perfect sphere. So what I'm interested in here is this what's called the ring down, the very last bit. So what's happened here is these 2 black holes, were in some highly excited state, and eventually they merge, and then they become a featureless sphere. And from Hawking, we know this is just a body in thermal equilibrium at some Hawking temperature. So it's just, and it's going to sit there forever, just as a featureless sphere. So I can just view, if I'm a quantum person, and I believe Hawking, then I can just view this process as the equilibration of some thermal equilibration of some object. So then I can ask, how long does it take to thermal equilibrate? Okay, so this is something you can compute from Einstein's equations. You get this number here. But then you look up the Hawking temperature from Hawking's paper, and then you realize that actually this time is precisely the Planckian time. Okay, so now this is the 3rd occurrence of the Planckian time, where now the temperature is the Hawking temperature. And so black hole thermal equilibrates as fast as possible, as any quantum system. In particular, which reaches this bound of the Planckian bound, just like the SYK model. And that's actually, it was, to me, it was the first hint that this model that I'd been studying a long time ago could be connected to some black hole physics because of this common time. All right, so that's a summary of all you really need to know about black holes, and really that they have an entropy, they have entropy for surface area, and they relax to thermal equilibrium in a Planckian time. Okay, so now let me make the connection with the SYK model a little more precise. So to make that precise connection, we have to actually consider a type of black hole that probably doesn't exist out there in the universe, a black hole which has a lot of electrical charge. So then you have to solve, to figure out how space-time curves near the horizon, you have to include Maxwell's theory of electromagnetism and Einstein's theory of general relativity. And then you solve it and you get some curved space-time. And then you imagine that you're, falling into this black hole. And for this particular charged black hole, it turns out that as you're falling into the black hole, as you approach the horizon, the universe would appear to have only the radial direction. Roughly speaking, all the important things are happening as you're falling in, and your angular motion becomes completely suppressed. So as far as you're concerned, as you're falling in, you'll view the universe as just have a line. You're just going in a direct line straight to the center of the black hole. So if you were, while falling in, working out the quantum theory of gravity, you would write down a theory which was lived in one space and one time direction, where zeta is this direction, zeta. And you won't have to worry about the angular directions at all. So there's your two-dimensional theory of gravity. It actually exists. It's a feature of, in our three-dimensional space-time. It's a property of Maxwell's electromagnetism and Einstein's theory of general relativity. But the only additional feature is that there's a net electrical charge in the center of the black hole. Most black holes are almost perfectly neutral, so that's why, but maybe someday people will see charged black holes. Okay, and it turns out that if you start from Maxwell's theory and Einstein's theory and you apply the Feynman prescription of working out the path integral, that's too complicated. Nobody knows how to do that. To really do it completely in 4 dimensions, you probably have to use string theory or something. But if you're satisfied with just looking at the one-dimensional motion along as you're falling into this black hole, then that theory turns out to be exactly the theory of the SYK model. Okay, there are some caveats there which I will discuss in my 3rd lecture. So here's a somewhat more technical way of showing it. This is the radial direction zeta that I showed you earlier. That's this direction, and I've straightened out this direction, x, which is now vertical x. So there's a sphere, S2 means a sphere. And there's my black hole horizon. And near the horizon, this is the metric. It's what's called ADS2. This is the space, one space and one time. And the angular directions make no difference. So I have quantum gravity in one space and one time. And then I can work out by the formula Hawking told me, the entropy of the horizon. And it turns out the properties of that entropy, in particular how it depends on the charge of the black hole, precisely coincide with the entropy of the SYK model. So as I'm falling in, it seems to me as if if I'm studying quantum effects, it's as if I'm just seeing the effects of a bunch of randomly entangled particles in this SYK-like state. Okay, that's the best I can do to give you an intuitive feel. Okay, so
Subir, there is one
yes?
question. Maybe it's the right time to ask this question.
Yeah, go ahead.
Sugar, you
see,
asked the question. Can you define SYK model in any dimensions?
Well, so the SYK model, as I've defined, is in 0 dimension, 0 space dimension, and 1 time. There are a lot of people who have worked in higher dimensional extensions, and they have closely related properties, but I want to just stick to the simplest case today. Okay, great. All right, so there's a connection between the 0 temperature entropy of the SYK model and Hawking's entropy of the horizon. But you can do better. If you remember, the formula I showed you had another path integral over this time parameterization f of tau. So you can ask, what is the correction to this one-dimensional universe that I'm seeing as I'm falling into the black hole? So in fact, if you look at the full metric, the full solution of Einstein's equation, when you're close to the horizon, you do indeed see a 1 + 1 space-time dimension. But as you go far from the horizon, you actually see our universe, 3 + 1 space-time dimensions. So space-time curves in this rather bizarre way where the effective dimensionality that you see around you changes as you fall into the black hole. So then there's a boundary where you go from 4 to 2 space-time dimensions. And it turns out that if you look at corrections to Hawking formula, the first correction comes from not what happens right near the horizon, but from the fluctuation of space-time in this region when you go from 2 to 4. So I'll show you in my third lecture how you can work out, in fact, the path integral of this boundary graviton. And that turns out to be precisely also contained amazingly in the SYK model. So the SYK model not only contains the Hawking entropy, but also the correction from the boundary graviton, which is a quantum correction. And that was shown by Keteev and Maldacena in Stanford. Okay. All right, so then moving on, I have about 10 minutes left. Is that correct, Jungkook?
You can take more time. If you want,
okay.
so we have more time.
All right, well, so I've talked about charged black holes and how if you just quantize or start with Einstein's theory and look at its quantum corrections, you can do that safely by just taking a theory of quantum gravity in 1 + 1 dimensions with this boundary. And you can write down the path integral over sum over all configuration of space-time as you must do quantum mechanically. Or you can start from the SYK model, which is much, much easier. I showed you the entire model. I didn't hide anything. That was the model. And you work out the path integral carefully, you get the same answer. So in some sense, the near horizon region of a charged black hole is holographically represented by the SYK model. Okay, so that's the very precise mathematical result that you can check by explicit calculations. One, you start from Schrodinger's equation for entangled particles. The other, you start from the path integral of Einstein gravity, and you get the same answer at the end. Okay, so since I have time, so my last topic will be about, that means, yeah, so, and why is this bizarre thing happen? Well, it happens fundamentally because the common feature is complex multi-particle entanglement, where you have a quantum system without quasi-particle excitations, and this Planckian time relaxation. And if you study, Hawking's computations of black holes, you find exactly the same features. And it turns out that this, it's a good lesson that when two things accidentally match in physics, there's probably a deeper reason for it. And that's what's led to all this progress in thinking about the holographic connection between quantum gravity and strongly interacting systems. Okay. All right, so now in the remaining few minutes, I want to talk about the last advertised claim in my talk, which is superconductivity, but maybe I'll pause here for questions on what I've said so far. Okay, then I'll proceed. All right, so now I guess let me emphasize that what I've talked about so far, is by this point, I think, a very well-established and precise mathematical result. It's not rigorously established, but it's checked numerically, and there's no doubt it's true. And it's a correspondence between a type of black hole that may not exist and a type of model that probably is very hard to make. So it's great fun, but we want to do better. We want to have actual experiments in the laboratory or with actual black holes. So I'm going to tell you a little bit about thinking about real superconductors. And there, many things are not understood, and I'm just going to tell you about some approximate results, which we think are giving us some insight. In contrast to my discussion so far, was really, by comparison, rock solid. Okay, so here's the type of material I want to talk about, called yttrium barium copper oxide. It has a complicated structure of elements and electrons moving around in a complicated way. Here's a little piece of it. It's a ceramic. It's not a very good metal, but when you dip it in a bit of liquid nitrogen, it becomes a superconductor. So here's a little cake of that. That's yttrium barium copper oxide, which was dipped in liquid nitrogen, which is in here. And these are a bunch of magnets. And because it's cold, it's a superconductor. And one property of a superconductor, in addition to conducting electricity without resistance, is that it hates magnetic fields. It expels the field. And so consequently, it'll keep going. Of course, you can guess why it crashed, because it heated up. It's not cold anymore, and then it just hits the tracks. All right. So that's a high temperature superconductor. If I was in Korea, I'm sure Jungkook would have provided me with a demonstration in the room. This is very easy nowadays to do this. So we want to understand, I mean, that's the big question. Why does this go superconducting at such high temperatures? I don't think we fully understand that today, but over 20 years, nearly 30 years of work have been spent studying these materials. And the goal is to make better high temperature superconductors, because they could be used in MRI machines and levitating trains and God knows what else. But while studying these materials, a lot of very beautiful, interesting physics has been uncovered. In particular, if you compare, these are materials in which actually exist, where many particle entanglement is crucial. And we're still trying to understand the nature of the many particle entanglement in these materials, unlike the ordinary metals I told about earlier. So fortunately, you don't have to study the full crystal. It turns out that everyone agrees from many experiments that all of the action is just in a single plane here, which is made up of copper and oxygen atoms. So here's a picture of the square lattice. So you have copper atoms at the vertices of the square lattice and oxygen atoms on the bonds. Actually, you can make life even simpler. You can forget about the oxygen, and you only need to worry about just one orbital on the copper. All the other electrons are quite inert. So in the end, you just have to worry about a bunch of electrons, where I'm just representing each electron by its spin, either up or down, sitting on the vertices of a square lattice. So there's an infinite number of them, and they're interacting with each other a lot. Now, it turns out that if you take a certain density of these electrons, you can vary the density by varying the oxygen concentration. There's a certain density where it's not a superconductor at all, but an insulator. Doesn't conduct electricity at all. And in the insulator, the electrons form what's called an antiferromagnet, where half of them point up on the black squares of a chessboard, and the other half point down, or vice versa. Okay, so this is an insulating antiferromagnet, which is extremely well understood and studied a great deal in experiments.
Subir,
So then,
one
yes,
question by Jae-dong No. Can I just repeat the question?
sure.
Many-body chaos and entanglement are generic feature of non-integrable system. What makes the SYK model so special that it describes black holes?
Excellent question. So if you have a generic non-integrable system, like any, like something, that has the Hamiltonian of sodium, it's non-integrable. So it does thermalize and has some entanglement, but it's rather limited. And in particular, the time to reach chaos is much longer than h bar over kT. So the Planckian time is the key. They take much longer, and the entanglement is not strong enough. So what's special about the SYK model is that they reach chaos and entanglement. They reach chaos in the Planckian time itself. So that's, and you do definitely need that for black holes. I mean, if you won't have enough entanglement if you just take a generic non-integrable system.
So, okay, great. So there are more questions actually. So one question from Han-son is how can you define surface of the black hole? Is it just the way we see the area of the black hole? That's the question.
Yeah, that's a good question. The horizon of the black hole is in some sense a bit fictitious. You know, if you have started looking at the black hole from outside, I can measure, you know, I can do experiments to measure the curvature of space-time, and from that, I can see where the horizon is. But if I'm falling into a black hole, I will see nothing special when I'm going through the surface. There's nothing there really. The horizon is featureless. The only singularity in the black hole is at its very center, where you'll be crushed mercilessly. But yeah, there's nothing actually special about the surface of a black hole.
There's another question. I think Professor Jian Che, you can talk. So I just unmute.
Okay, thanks for giving this opportunity. Okay, so basically I have one simple question, which is just you saying that your model follows the Area's law, and then can we just imagine that you can extend and state that any system which follows the area laws of entanglement can have analogies of quantum gravity in 1+1 dimensions. For example, you know, this like many-body localization system also follows the Area's law. And I wonder whether there is kind of analogies of in the system to the quantum gravities.
I don't think so. Let's see, a many-body localized system is in some sense integrable. Now, I'm not sure. So the point is that in this case, it's the entropy. The entropy of a many-body system, many-body localized system, is a volume law. The entanglement entropy is area law, but that's true for any system. Okay, so it's So in some sense, in black holes, the feature is that the entropy is equal to the entanglement entropy, which is not really true for other systems.
Okay, thank you.
There is another question. I just unmute so you can.
I mean, these are all questions on black holes, which is great. I guess maybe we'll just get the questions on black holes now, and then I'll just say a few things about superconductors. Okay, yeah, please go ahead.
So I cannot read the name actually. So that, but okay, let me just ask the. So I'll just read the question. So, is there any theory?
Yeah, I can read it.
So you can read it. Okay, go ahead.
Yeah, is there any theory on black hole with bosonic entanglement? And will it be the same consequences as fermionic entanglement? So yes, you can make a generalization of the SYK model with bosons. In fact, our very first paper in '93 had such a model there. But you need bosons with many, many flavors. So it's more complicated. It's much easier to do it with fermions. Because the trouble with bosons, they just want to both condense. And then, so you have to really work hard to stop them from condensing. With fermions, that's not a possibility. So the only thing you have to do is make sure they don't form quasi-particles. More questions on black holes, and then I'll talk about superconductivity. Why does the existence of quasi-particles imply limited many-particle entanglement? Well, because I can describe the time evolution of the system just by following each quasi-particle independently. So I don't have to worry about the entanglement between different quasi-particles until they start colliding, but that collision time is so long that over an appreciable time, the quasi-particle is well defined. Second question, since the SYK model is described in 0+1D, do the placement of the sites matter since all are connected? No. Or does the coupling constant between the sites depend on locations? Well, in a real world, yes, it would depend on the locations. So that's why when you're making one in the lab, you have to worry about exactly where you place them. So that you get something that's similar to the fully random connection. But in the model I defined, no, the placement was just to to draw something, I could have put them anywhere. But that's just a model where I just by hand said that the couplings are random. In the real world, we would have to just figure out how to place them. Yeah. Okay. All right, great. Okay, so let me get to my favorite topic, which is superconductivity. So as I said, it's this material that floats around, and there are these copper sites which have electrons that form this antiferromagnet. And then, but that's not a superconductor, it's an insulator. Then what you have to do is just remove a few electrons. Our density of what we call holes is P. Some P is some small number. So you can do this in the experiments by some clever chemistry. And now the electrons can move around. So now you have these, because the holes can move with no trouble, there's no repulsion between between electrons. And the amplitude for this process is T. And not only can they move with T, but they can exchange the spin. So that's another thing that's important for the real world. The spins of these electrons can exchange. And so now everything gets entangled. And the question is, how do you describe this model? Well, that's easier said than done, because this is a question that's in some sense been open for 30 years. It's much harder to solve than the SYK model. But we'll try to, in the few minutes remaining, just make a toy model which captures some aspects of this. Okay. All right, so now let's show you the famous phase diagram. So this is on one axis, the density of the holes, P. On the other axis, temperature. Here's the insulator that I began with when there were no holes, and P was 0. As the antiferromagnetic insulator. And then when you increase P, you get the superconductor. And you notice the superconductivity appears, temperature about 100 Kelvin in this particular phase diagram. Could be even a bit higher. All right, so people have been studying this region here a lot, which is described by that model I just showed you, sometimes called the TJ model. And a whole, many, many beautiful things have been discovered, which are not shown in this phase diagram. But roughly speaking, if you look at this region above the phase diagram, you find 3 different types of metals, which I won't say much more about, other than say that this Fermi liquid is where quasi-particles exist, and things are perfectly well understood. The pseudo-gap metal also quasi-particles exist, but they still behave in some bizarre way. But I just want to say just a few things about the strange metal. Somebody should come up with a better name, but that's what we call it, which happens roughly just above where the TC is the highest. So this is really the most interesting metal, because that's the metal which gives you this high temperature superconductivity. And again, there's literally thousands of experiments been done on this strange metal, but I'll just show you one, not yet published, some very beautiful work by the Sherbrooke and Cornell group, where they measured something called angle-dependent magnetoresistance. And through some very clever analysis, they were able to track out from this famous time tau that I mentioned right at the beginning. What is the scattering time of whatever is moving the charge around in a magnetic field? And amazingly, if you pull out certain anisotropic terms, which we have good reason for pulling out, you get an isotropic scattering time, which is, again, the famous Planckian time, with a coefficient here of 1.4, or the inverse of the Planckian time here, because it's the inverse of time. And that, immediately sets off alarm bells. In fact, measurements like this have been around for a while. And it was because of, I was in 93, this was also known roughly. I was trying to come up with models that have this behavior. And that was the origin of what was initially called the SY model, and then became the SYK model when the connection to gravity was sharpened. All right. Anyway, so so that tells you maybe there's something to do with the SYK model. We don't know what, really. That's the honest answer. But maybe we should take some inspiration from the SYK model to understand why this is going on. So I'll just tell you about our recent latest attempt, which we're pretty excited about. This is work with Antoine George's group at Flatiron, and postdoc there, Alex Vitek, and my student Henry, and also some more recent work with my student Maria and student Hayu and postdoc Grisha at Harvard. So what we do is we take, this was the TJ model I showed you earlier of electrons hopping around and exchanging spin. They were doing that on the square lattice. So what we're going to do is keep all of that so that each side can either be empty or have a spin up or a spin down. We keep all of that, but just throw away the square lattice. We'd love to solve the square lattice, but it's just too hard. So we just say maybe the square lattice is not so important, and let's just take, in the spirit of SYK, a model where anybody can hop anywhere. So for example, this electron can hop there, this electron can hop there. All of this is allowed. And every one of those, in fact, you can take them random or not random in this case. And also spin exchange is allowed between any pair of electrons. And that we take to be a random number. So that's the model we look at, TJ model with T and J totally random. Okay, sounds like a silly model, but the question is, by simplifying so much, have we completely lost the physics? And we strongly believe you haven't. So we studied this model in some detail through a variety of methods. And since here I'm going to get a little technical, so I apologize. We compute something called the dynamic spin susceptibility, which is basically a measure of how many spin excitations do I have with the frequency omega. So if I send in a neutron and flip the spin of an electron, what's the probability that the neutron will scatter and lose energy omega? Roughly, that's what this quantity is. And as a function of hole density, you get these various curves. This is from numerical study of this model. And what you see at low doping, when P is very small, you get this very large peak at low energies. And that tells you this system is a glass. The spins are just freezing into some kind of glassy behavior. That's not so interesting as far as Planckian behavior is concerned. But above, that only happens for P less than some critical PC. But right at PC, we find, in fact, it has the same spectrum, a constant minus omega, which I'll say more about in my last lecture, or the third lecture, which you get from the SYK model. It has exactly the same. In fact, it just matches the behavior of the SYK, even though this is a much more complicated model, much more realistic. And furthermore, if you look at how it depends on temperature, you do indeed find the Planckian time emerging, and even some corrections, which can be viewed as corrections from the boundary graviton dual. And this appears in the model where you just took the TJ model and just put it on a random cluster. All right, so I'm going to say much more about this in, I guess, my last lecture. So there's many features of this random TJ model which agree with many aspects of the experiment. So unless, if you just take away all the parts of the experiment that are sensitive to the square lattice structure, everything else seems to match the experiment, including this Planckian criticality. Okay, so that was fast. I'll say more about it. But as I emphasize, this is, our attempt to solve a very difficult problem where we're pretty excited about the progress you can make by taking this random TJ model. Okay, so that's the conclusion. Talked about quantum entanglement, how it plays a role in the SYK model and charred black holes, and the progress we hope in understanding the real world in the copper-based superconductors. So the connection, these two are both different realizations of 2D quantum gravity, and this model seems to model reasonably well what you observe, at least near critical doping, in the copper-based superconductors. And the common theme, I'll show you again this slide, is the absence of quasi-particles, many particle entanglement, and this Planckian time. So thank you very much.
Okay, yeah, thank you for a very nice talk. If there are questions, I think it's a good time to ask questions. So you can just raise your hand, or oh yeah, yeah. So I just allow if you raise your hand, then I allow you to talk. So you can unmute and you can just speak.
Oh, sorry. What did I do?
Okay. Can I ask you?
Yes, I can hear you.
All right.
Go ahead.
Hi, Subir.
Hi.
So, what is the actually essential ingredient of the theory where the Planckian time appears? Is that the strong coupling, or do you think entanglement is more important there? Or both?
Well, so many ways to understand it, but roughly speaking, it's kind of the scale invariant structure of the entanglement. So one way to think about it is that if you think in terms of renormalization structure, you have some set of interactions and they flow to some fixed point. And then that fixed point is universal. So there's a scale invariant structure of the entanglement, and therefore the only scale then you have left over at any temperature is just temperature only. There's nothing else. Now, it's not sufficient to have scale invariance. It has to be scale invariance and strong coupling. You could have a, like free Fermi gas is scale invariant, and it doesn't have Planckian relaxation because it has no relaxation. So the other possible answer, if you have a scale invariant theory, is either Planckian time or infinite or zero or something. So you need both strong interactions and scale invariance. Yeah. So,
and entanglement is not something which is directly relevant, you say?
Well, I think, if you're asking, are you asking that will I find Planckian time in a system that doesn't have
Yeah, right.
entanglement?
Yes.
I would say no, because I would say this is somewhat of a conjecture, but I would say that if you have a system that doesn't have strong entanglement, what that means is that you can think of it, there must be some quasi-particle description of it. So what is of a quasi-particle description in the most fundamental sense? A quasi-particle is an additive excitation. That is, you could have excitation of one particle here and excitation of other particle here, or you can have them both. So you can add two excitation to create another valid excitation. So when you can add excitation and create more excitations, then you automatically have quasi-particles. That's what a quasi-particle is. It's the basis for the many particle states. You can add and subtract them to get other states. And because you can add them and subtract them, it automatically means that they're not really entangled. So what happens in a system with strong entanglement where there are no quasi-particles, then each excitation is totally independent of the other one. And that can only happen if you've got a completely different wave function, meaning you have strong entanglement. But once you have quasi-particles, by definition, you cannot scale. They last a long time, and so your equilibration time will become longer than the Planckian time. So that's kind of my physical attempt to understand this. That I don't think it's possible to get a Planckian time in a system that has a quasi-particle basis.
Thank you very much.
So it's a conjecture that every system that saturates the Planckian time has no quasi-particles. I made this conjecture a long time ago, and so far no one's found a counterexample. And I'm pretty sure there isn't.
All right.
Any other questions, especially from students? Okay, so there are questions. Okay, good. First, Professor Yoon-Gyu Pang.
So before I ask my question, let me just continue another question, continuing from Professor Sang-Jin Shin's question. So when you define this relationship between quasi-particle, existence of quasi-particle and entanglement, this argument is related to the definition of your SKY model. To my
I mean, the aspect, so I would say that, I gave some general arguments just a few minutes ago.
No, my question is very simple. So let me go on.
Go ahead. Please, sorry.
So when you define your model, I think I remember you didn't allow single particle hopping or single particle scattering. Is it related to by definition you don't allow quasi-particle, the existence of quasi-particle? I mean, when you don't allow this single particle hopping, it automatically you prohibit the presence of quasi-particle?
Well, I mean, that was not obvious until the model was solved. I mean, that was the insight of the model.
What was your
but if you
yeah.
Well, my original motive, I was looking at a slightly different model with spins.
I see.
So my original motivation was a bit more physical, in fact, than the SYK model, which is a lot easier to solve. Basically, I took exactly this model here with random Jij.
Right.
And my motivation was precisely the cuprates. But then to get the non-quasi-particle state and not a spin glass, I had to generalize the group here from SU2 to SUM. So it's a bit more complicated.
I see.
Now, if you take the SYK model and you include single particle hopping, yes, you will get quasi-particle. You can solve it and see that you get quasi-particle at low energies.
I see.
It is, and now the insight, the contribution of this is that all you have to do is set the single particle hopping to 0 and take random couplings, and that gives you finally really the first solvable model of a quantum many-body system without quasi-particles.
I see.
That it wasn't obvious at all. And I think we're learning a lot from just studying this toy model and all its connections to many other more realistic models.
So once you allow this single particle hopping, then your model immediately goes to ordinary quasi-particle metallic system?
So the SYK model, yes. Okay. But it turns out if I take this model, the TJ model, and I include single particle hopping. So this is a much more physical model. It's got both single particle hopping and this kind of spin exchange, which is like a two particle term.
I see.
So now here's a model which has both single particle and two particle, and that's really why I'm excited about this.
I see.
And in this model, generally it does have quasi-particle or it has spin glass or something. But it seems from our numerical study, and we have some analytical support for that, it seems that there is a critical point in this model at PC. There's a critical doping where it looks like essentially like the SYK physics, even though it has single particle hopping. So that's what's, I think, exciting about these more recent results.
Okay.
It's a good question. Thank you.
So then here is
this last part was fast.
Here is my own question, actually. So in your model of random TJ model, what parameter or what aspect determine this critical doping P star? I mean, this P star is just I mean, there should be some parameter which determine this P star in your model. Is it?
So so there is one parameter which is the T over J, presumably determines P star. We don't have enough data to know exactly how it depends on P star, but it turns out the P star that we find are all around 0.3 or something like that, 0.3 to 0.4. And there's a very simple way to understand that. So, which actually becomes exact in a certain limit. So the key feature of the TJ model is that 3 states on each side, empty, spin up, and spin down. So now just focus on one side and just very crude argument. This is just, extreme. This is the world's simplest argument for the value of P star. suppose these two states, of course, they have to be degenerate because they both have a spin symmetry. Suppose these two states are lower than that state. Well, then they'll be more occupied, and so there'll be some spin sitting there. Most likely that will become a spin glass. On the other hand, if this state is lower than the other one, then you can see by a similar argument that you just get a Fermi liquid, because this thing can move around quite freely. However, if the three states are degenerate,
Right.
then we think we get a critical point. So if the three states are degenerate, then the density of this state is 1/3. So that's why P star is close to 1/3.
So then, according to your argument, this P star doesn't depend on T over J?
Now, this is a very simple zeroth order argument. I'm sure there'll be some corrections that depend on T over J in this model. So, but anyway, in this random TJ model, and indeed we found him, we had made this argument before, and then we did the numerics, and indeed we find it's not too far from 0.33 PC. Yeah, right there.
Great. Okay, thank you very much.
Sure.
There are two more questions. Purum No, Heist student.
Thank you for giving wonderful lecture.
Thank you.
There is some relation between superconductor and SY model, and there's also some relation between black hole and SYK model. So does it imply that there is a relation between superconductor and black hole? I mean, can we understand black hole from superconductor?
Not too literally. I think I would say that the connection. So if I look at this phase diagram, oops, sorry, I went the wrong way. So if you look at this phase diagram, I'm really talking about the strange metal, which is present above superconductivity. And then you could imagine perturbing the strange metal to get a superconductor. I really didn't talk about that. So I would say, yes, there is some connection between strange metals and black holes. They are both systems which have strong many particle entanglement. They have Planckian time relaxations. And under very special circumstances, one is explicitly equal to that, as I showed you in the first part of my talk. But I would say, it's not too literal. It's not as if suddenly my superconductor is going to start looking like a black hole. I'm not. That's not how literally you should take it. I would say that this is my best summary. So these are systems that have these features, that have entanglement, they don't have quasi-particles, they have Planckian time relaxations. Now, so these common features lead to some similar set of equations that describe their time evolution. Now, it just turns out that for charged black holes at low energy and the SYK, the artificial SYK model I show you, the equations are exactly the same, which is quite amazing. But there are variations in the equation. They can be slightly different. And so I seriously doubt that even the strange metal of a cuprate has somehow exactly dual to some black hole. I don't think so. But it has a lot of similar properties like the ones I've just been discussing.
Thank you.
Okay, next BJ.
Yes, you had a slide on dynamic spin susceptibility. I didn't quite understand how does the Planckian time manifest in the spectrum? And,
okay, good question. That was very fast. I'm going to say much more on this in my fourth lecture, actually, the last lecture. So this is the dynamic spin susceptibility that we measured in numerics at 0 temperature. Okay, and it has this linear in omega term. And that linear constant plus linear in omega term perfectly matches what we get from the SYK model. And then, as I'll show you in my last lecture, we can start from the SYK model and compute the finite temperature behavior. And then we see the Planckian time. So that's a computation. Now, what we could do, and we did do some of this, but the data wasn't good enough. Just compute this at finite temperature from our exact diagonalization and see if we see a Planckian time. We didn't have, we couldn't tell really very clearly from that numerical data, but
so
we fully expected
what
to be
unit
there.
are you measuring omega with?
With the temperature, that's all.
But that's a zero temperature spectrum.
It doesn't. I know. So you have to take this spectrum and do it at finite temperature. Actually, I just, sorry. So with our exact diagonalization results, we could not get enough precision in our finite temperature results to see the Planckian time. However, there's another paper coming out very, very soon by the Flatiron group, Antoine George and others, Olivia Parcolet. And they use a different method to analyze very closely related model, essentially the random TJ model, with a different method. And they can compute it finite temperature properties. In fact, pretty much the imaginary part of the electron self-energy they can compute. And they very clearly see a Planckian time. So that, yeah.
I see. I presume this is the zero momentum spectrum.
So in this case, this is a random. There is no momentum. It's a local. It really should be thought of as the momentum integrated spectrum. It's the local spectrum. It's the momentum integrated spectrum. That's what we compute in this random model, but you can compute other things too. It's basically momentum independent in this simple model.
BJ, do you have more questions?
No, thank you. Thank you very much.
Then next, Hanbin.
Yes. Thank you for the very fascinating talks, and I have a few questions. The first question is about the SYK model, and actually you did not mention about SYK type criticality in this talk, but I want to ask about it. So, can this type of criticality be changed when we change the statistics of random number in SYK model? It is because the conventional disorder system, the fixed point can be changed when we change the potential of disorder based on Harris criteria. So can you give any comment about it?
Okay, your question is, can you tune the critical point by varying numbers? Is that right?
Yeah. If we change the statistics of the SYK model.
If you choose different set of random numbers, will things change?
Yeah, not the Gaussian, but any other statistics.
Yes, the answer is no. It doesn't matter. As long as the couplings are independent random numbers, the answer is pretty much the same. You can take independent random numbers for 2-body, 3-body, 4-body couplings. It will always have the same low energy behavior, which I will write down explicit equations for spectral functions and all of that, I think in my lecture 3, but you have to wait for that. I try to really minimize the equations here, the first colloquium. So yeah, but I will go into some of that. Yeah.
I did not catch the reason of the reason, but can you?
It's like a central limit theorem. I mean, you have a central limit theorem with lots of self-averaging here. So basically, the idea is that, if I go back to the original SY, oops, I always keep going the wrong way. Sorry. Let me just
you mean that if the centralized limit theorem is working, then the higher moment is not that important, but the second order moment is important. So other higher moment is not important. Is it right?
Yes, exactly. But here, in fact, it's even better than the central limit theorem. Here, the convergence is much more rapid, but it's in the same spirit. I mean, roughly the idea is if suppose I'm sitting looking at this site,
yeah,
and looking at its properties, by some measurement. Well, this site has coupled to every other site. So there's an n squared set of random numbers associated with that site. So it turns out that I only need to take one sample, and it has the property of self-averaging. Even in one sample, it self-averages very, very quickly because Hilbert space is exponentially large. That's the key difference from ordinary statistics. Here, we are talking about statistics in Fock space of which is exponentially large, e to the 10 to the 23. And because of that, every site actually looks exactly the same as every other, even in a given sample. You don't have to do any averaging. You just take one sample with a set of random set of numbers, and that should have the same properties.
Thanks. And I have a second question.
Maybe we can see whether there are people who want to ask questions a bit, if you don't mind.
Yeah.
Are there any people who want to ask questions? Since we have some time, it's already 1.5 hours. But we have a little bit of time, so if you want to ask question, it's good time. No, then dear,
Go ahead.
yeah, go ahead.
Okay, so I guess you will explain later, but whenever your slide had S0, does it depend on like how many which many-body interactions I include? Like, for example, when I have like 4 fermion terms or like 6 fermion terms, would S0 depend on like 4 or 6 or?
Well, if you have yes and no, if you have both 4 and 6, then the 6 won't matter at all.
Sure.
Only depends on the smallest number.
Yeah.
So the smallest number.
I see. So it depends
on. So it's a pure
Q.
number. It depends on Q. But higher Q terms will not change it. It's universal. It's a property of the low energy fixed point, and the low energy fixed point only determined by Q. That's all.
Okay, thanks.
Since it is brought up, can you comment on this S0 and the third law of thermodynamics? Maybe so in the third law, we learned that entropy goes to 0, but here it seems more interesting. Can you comment on this?
Yes, sure. But it depends a little bit on what you mean by the third law. Okay, so if by the third law you mean that it's a question of order of limits. If you take a finite system n, and then you take temperature to 0, then the third law would say that, well, the ground state, you have some finite degeneracy of the state, and therefore the entropy cannot be macroscopic. That is obeyed by the system. If I take a finite system and temperature to 0, then you will find that the entropy is 0. However, if you do the opposite order of limits, you first send the system to infinity and then send temperature to 0. Then in most systems, what happens is that the entropy still vanishes. And that's for a different reason. What happens if you have a many-body system, you have, system of size n, then the spectrum has width of order n, the many-body states, but the spacing between the states is e to the minus n, because there's e to the n states. So very, very finely spaced states. However, in a typical system, when you go to the ground state, the spacing is no longer e to the minus n. It's of order 1 over n or something. And that's why the entropy vanishes. So the SYK model has a special feature that this e to the minus n spacing of states is present not only at high energies, but all the way down to the ground state. So the ground state is kind of like a thermal state. It's not special compared to any other state. Yeah, so that's a feature of the SYK model. It's also a feature of charged black holes, actually. And you can call it a violation of third law of thermodynamics, but you know, the third law is a conjecture anyway. So this theory, this thing, it actually happens. Numerically, it's been tested. So, you know, we actually, I should say, you know, this S naught was computed by, oh, I forgot to put the reference. Did I? Yeah, okay. It was computed by Georges Pacollet and myself in 2001. Yeah, we found this S naught and we said, okay, this is bizarre. It's never going to be seen. We put it in appendix. So we were ashamed of it. But this was actually the most interesting thing in the paper. And now, since then, you know, after Kitaev's simplification of the model, you could put it on a computer and numerically diagonalize it. Yeah. And you diagonalize the SYK model and you check it, and it indeed, you can measure S naught. And in fact, our value of S naught was bang on, it was correct. And you can now see it numerically in exact diagonalization of the spectrum of this Hamiltonian. So there are certain Hamiltonians which don't have a sense of space. So it's really a zero-dimensional system. I think that's important here, which can violate third law. You know, third law is not a law. At least it doesn't apply to the system. There's no question about it. In finite dimension, if I take finite dimensional models, then you don't get this entropy. And in fact, the TJ model I talked about, even the random TJ model, probably doesn't have this entropy. It has many other features, but not the entropy. Yeah, yeah, that's something that we're still trying to understand.
So this reminds me of this classical spin ice. So they're a huge.
No. Classical spin ice is totally different. Yeah, there it's so there's something. Yeah, there's the spin ice has entropy. Yeah. Because of some degeneracy. Yeah. Right. But that entropy is infinitely sensitive. You change one thing, you change even one coupling constant in the Hamiltonian, right, the entropy disappears. Yeah. So it's that entropy of spin ice has an infinite number of relevant operators. One way to say it. This entropy has only one relevant operator, which is the single particle hopping. You can change all the couplings, nothing, it's still there. It's very robust. Unlike spin ice entropy, which is not robust at all. It requires infinite fine tuning. This requires only one tuning, which is no hopping.
Any other question?
I have a quick question.
Sure, go ahead.
It is my second question. So you show the spin susceptibility data at the end of the presentation. And if the doping ratio P is smaller than the critical P, then the spin glass already appears. So my question is that, is this spin glass phase is insulating phase? Or
no, it's a metallic spin glass.
So it is metallic. So the Fermi surface is large.
No, it's probably we can see it's small. I don't show this data, but that's in the paper. So we think the spin glass phase is a good toy model for the pseudo gap for this region here. It has a small Fermi surface, and there's above PC we see a large Fermi surface. Yeah. Sorry, I didn't go to those details, but my last lecture, if you're still interested, will say more about these points.
Yeah, I will take that lecture. So, thank you.
Any other question? It seems like there. Okay. Hyuk-jun, please speak. Hyuk-jun, can you you can talk.
Yeah, thank you. In the strange matter, it seems that because of the Planckian scattering rate, it seems there is some kind of strong scattering mechanism in the strongly correlated phases, then can we say that the deviation of the critical exponent of the resistivity from the usual Landau parameter liquid can be some kind of measure of quantum entanglement?
Yes. I mean, I would say that, that's the kind of the logic to this last slide. So you're saying, all right, when we see deviation from linear from t-squared resistivity, that means there are no quasi-particles. And I gave this argument, I think, in response to the first question, Sanjin, I think was, then absence of quasi-particle pretty much implies complex and multi-particle entanglement. Yeah. I mean, this is not a rigorous statement, but I think you can make quite a strong argument for that.
Yes. So, yet is there no explicit relations between the deviations and the quantum entanglement? It is.
Well, I mean, I think no, there's no explicit proof, but these are. Yeah. But all we can do is solve many models. You keep finding more and more models that you can solve, and I've yet to see a model that has linear resistivity which has quasi-particles. There are some artificial models that are not very robust, but I think in all the cases we've looked at, these claims I'm making here hold up. But yes, it's not a rigorous proof of any type. I would say the best we have for a rigorous proof is the paper of Maldacena, Schenker, and Stanford on the chaos bound. That's not also entirely rigorous, but it's quite rigorous. But it takes not a transport time, but it takes chaos time. So it's not a easy thing to measure, but if you take that time, you can establish things rigorously. Establishing something for transport time is a much harder problem. Yeah.
I see. Thank you for explanation.
Sure.
Any other questions? No? So.
Okay. Well.
Thank you very much, Sir.
Thank you very much.
So I think we will have more time to ask questions. Personally, I have several questions, but since I'm the chair of this session, I will ask later when I'm not doing the chair.
Could I ask general question?
Sure, go ahead.
There are so many and deep stuff to study for being a theoretical physicist. So could you give me some advice to acquire this knowledge effectively and wisely?
He's the first year student. So he's the first second year. He becomes second year soon.
Yeah. Well, I don't know. I mean, you have to, of course, take the basic courses and learn the basics well, but find something that excites you and interests you, and keep following it, and don't believe everything you read in the papers. Many claims are made that may not be right. So trust your own intuition. Go to seminars and talk to Jungkook. He can give you good advice.
Yes. Thank you.
Okay, so Sopong, okay, so I'll unmute you. I allow to talk. Okay, Sopong, please ask. Speak.
Yes. Oh, yeah. Thank you for the wonderful colloquium. So my question is, so I mean, it seems like the overall story here is that if you have a scale invariant system and which is strongly correlated, you're going to have this kind of ADS-CFT structure to your entropy. So
no, only in 0 dimensions probably. Yes. Okay. No, continue. I'm not sure what you meant by ADS.
So the second question is, I mean, does this Planckian time being the thermal equilibration time, is that, I mean, is this show? Can it be shown that this is a sufficient condition for determining that this is a strongly correlated? You have a strongly correlated system.
Depends what you mean. I mean, for example, if I take the 2+1 dimensional Ising model as critical point, which is a CFT, it's a Wilson-Fisher CFT, that will have this Planckian time, no doubt about it. It's a CFT, but is it dual to weakly coupled theory of gravity? No, probably not. I mean, it can be represented as some theory in ADS, but it's a very strongly coupled theory in ADS, so it's not necessarily then a weak black hole. So yeah, you know, I think right. So the many systems that have these properties I've summarized here, and you know, the SYK model in some sense is the simplest one, and it's really the only one that's solvable, and it's also connected to black hole physics, and it's been very useful for black hole physics. But I'm certainly not claiming that every system that has these properties will be a dual to weakly coupled black hole. It's certainly not the case.
Okay, so
yeah, I mean, I think the black hole connection is useful because it's another solvable limit. So if you could start from some model, you say you want to learn something about the Ising model, you know, sometimes we take a large n limit, and then we learn something from the large n limit, and then we extrapolate to n equals 1. Similarly, you could take the Ising model and embed it in some supersymmetric limit, and then get the black hole dual, and then try to understand something about what's happening at small n. So one could just view the black hole from this point of view as just yet another solvable case that you should have in your arsenal, because it helps you with many other tricks that you're using to solve these systems.
okay, but you also mentioned this possible extension. I mean, you mentioned zero-dimensional case for the SYK model, but you also previously mentioned people trying to obtain like a higher dimensional extension of this SYK model.
Yeah.
So
yeah, well, those are not generic models. They're rather special types of models. Yeah.
Yeah. So I mean, what kind of criterion are they satisfying that makes this kind of higher dimensional extension possible?
Well, there are many different models, but what they're trying to do is kind of retain the solvability of the SYK model, and at least get some intermediate temperature range where you have this Planckian behavior, and see what you get there. They all have some amount of fine tuning or something artificial. You know, we still, you know, we don't have a solvable model that I can just say, oh, this is describe the cuprates. We're not there yet, but we're getting close. I mean, I think we're getting many models that have such behavior, and they're not fully realistic yet, but yeah. I'll give you some survey of some of the models in, I think, my last lecture. Yeah.
Okay, thank you very much.
Sure.
Other question? No? No other question? Yes. Then it's already 1 hour and 15 minutes. Thank you very much, Sugir, for wonderful talks and this Q&A session. And we will see you tomorrow morning here and tomorrow night there.
Okay, well, thank you for listening, and look forward to the next one.
Okay.
The next lecture will be, you know, more at a seminar level, a little more technical, of course. Yeah.
And I think there are people who are interested in cold atoms. They will join also.
Yeah, I will say something about cold atoms in the next lecture. Yeah.
Okay.
Thank you very much.
Thank you.
Okay, thank you. Bye.
Okay, bye. Great.
Right. Bye.
Okay, thank you.
별 문제 없이 잘 지나가는 것 같습니다. 내일 박봉 교수님한테 제가 좀 부탁드리겠습니다.
네, 알겠습니다.
네.
네.
감사합니다.
예, 감사합니다.
네, 수고 많으셨습니다.
예, 그럼 내일 봬요.
네,
내일
뵙겠습니다.
뵙겠습니다.
네.
네.